Okay, so good day everyone. My name is Joylyn A. Zapico, a BSCE 4A student, and I'm going to discuss to you about the vertical stresses in soil. So what is vertical stresses in soil? Before we proceed with that, let me discuss to you first what is soil and its relation to our main topic. So soils are multi-phase systems. In a given volume of soil, the solid particles are distributed randomly with void spaces between. The void spaces are continuous and are occupied by water and or air. In an original soil, it obviously is impossible to keep track of forces at each contact point. Also, it is necessary to use the concept of stress. So the stresses within soil are geostatic stress, a subsurface stresses caused by mass of soil. Next, the stresses due to surface loading. So for our geostatic stress, we have the vertical stress and horizontal stress. For our stresses due to surface loading, we have the rectangular loaded area, infinitely loaded area or the filling, the point load or the concentrated load, and lastly the circular loaded area. So when we say vertical stress occurs due to internal or external applied loads such as overburden pressure, weight of structure, and earthquake loads. So back to our main topic, vertical stresses in soil is the vertical stresses in soil at any depth can be computed by considering the weight of soil above the depth. So as we see in the figure, if the unit weight of the soil is constant with depth, the formula is equals to vertical stress is equals to delta times z, where z is the depth of the point considered and delta is the soil unit weight. So for our layered soil, we have the formula, the first and second formula, and if the unit weight is varied with depth, then we can use this formula. So in this figure, we have the soil 1, soil 2, and soil 3 that represents the C sub 1, C sub 2, and C sub 3, same as delta sub 1, delta sub 2, and delta sub 3. So we have three components of vertical stresses in soil. In saturated soils, the normal stress at any point within the soil mass is shared by the soil grains and the water held within the pores. First is the effective stress or intergranular stress. It is the component of the normal stress acting on the soil grains. Next is the pore water pressure or neutral stress. It is the remainder or the normal stress acting on the pore water. Last but not the least is the total stress. It is at any point within the soil mass, and so the formula is total stress is equals to effective stress plus pore water pressure. Just a reminder, those three, it only applies to normal stresses in all directions at any point within the soil mass, while in dry soil, there is no pore water pressure and the total stress is the same as effective stress. Okay, so let's proceed to sample problem number 1. For the soil profile, calculate the vertical stresses at points A, B, and C. Okay, so for our given, for our delta sub 1, we have the 16.5 kilonewton per cubic meter. And for our C sub 1, we have the 6 meter. For delta sub 2, we have the 7.8 kilonewton per cubic meter, and C sub 2 is equals to 13 meter. Okay, so this is the figure. As you can see, we have the point A, B, and C. Okay, so for the solution at point A, since point A is the first point and it was placed in the ground, so Z is equals to 0, then our vertical stress is equals to 0. So at point P, vertical stress is equals to delta times C, then it equals to 16.5 times 6, then we have the result of 99 kilonewton per meter squared. So at point C, as we can see in the given formula, we have the 16.5 times 6 plus 17.8 times 13, then it come up with 99 plus 231.4. Then if we add that, we have our final answer of vertical stress is equals to 330.4 kilonewton per meter squared. So we have our answer at point A, point B, and point C. Then for our sample problem number 2, for the soil profile, calculate the vertical total effective stresses and pore water pressure at points A, B, and C. So for our given, as you can see in the figure, we have also the point A, B, and C. At point A, we have the dry sand. At point B, we have the saturated sand. Then at point C, we have the saturated clay. Okay, so for our solution, at point A, since point A is in the ground, then all our final answer in total stress, pore water pressure, and effective stress is all equals to 0. Okay, so let's proceed to our point B. At point B, we have the formula of total stress is equals to delta times C. And we have 16.5 times 6 is equals to 99 kilonewton per meter squared. So we have now our answer to total stress. So for our pore water pressure, our final answer is equals to 0. Then for the effective stress, as you can see in the given formula, we will subtract the total stress and pore water pressure. So we have 99 minus 0, then our final answer is 99 kilonewton per meter squared. So, then we will proceed to point C. For our total stress, we have the 16.5 times 6 plus 19.25 times 13. Then, if we multiply each of that, we have the 99 plus 250.25. So if we add that, we have now our final answer in total stress at 349.25 kilonewton per meter squared. So for our pore water pressure, since we have given, then 13 is multiplied to 9.81, then we have 127.53 kilonewton per meter squared. Then for our effective stress, we will also subtract the total stress and pore water pressure. So we have 349.25 minus 127.53 is equals to 221.72 kilonewton per meter squared. Okay, so as we get our final answers at point A, point B, and point C. Okay, so that's all, and I hope you have learned about my topic. Thank you.